तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last couple of classes, we have been looking at the numerical methods to calculate integrals of a function. That is, we want to evaluate the integral of a function which is between the limits a to b f of x dx, and we call that as I of f. So that is what we have been looking at. So, we have been looking at a calculation of this quantity f of x dx as of for any function f. Okay. So, we looked at various methods for doing such integral, okay, and some of them I will just summarize here. Is one is the what is called the rectangle rule. Okay. So, in this rule we approximate the function the integral of the function by the function evaluated at one point multiplied by the whole interval b minus a. Remember, b and a are the limits of this integral. So, it is integral a to b, and then we evaluate the function at the first point a and then multiplied by the interval b minus a. So, that is one method which we learned, and then another method again which involved evaluating the function only at one point, which is now in between a and b, that is a plus b by 2, and multiplying it by the interval b minus a. So, that is again another approximation. We call that as a midpoint rule. These are two methods which involve evaluating the function value at one point, and then there were other methods which is involved for evaluating the function at 2 points, and one is trapezoidal rule. In the trapezoidal rule, we approximate the integral of the function in the interval a to b by f of a plus f of b, that is evaluated at the two ends divided by 2 into the interval b minus a. So, this is three methods which we looked at using called the rectangle rule, midpoint rule, and trapezoidal rule. These are all of methods which are polynomial of order 0, okay, approximation to polynomial of order 0. And then we looked at this first two methods of polynomial of order 0, and this is 0th order polynomial, this first order polynomial, and then we looked at the next order polynomial, which is the Simpsons rule. So, now that involves evaluating the function at three different points, that is f of a, f of b, and f of a plus b by 2. Now, we will evaluate the function at the two ends and also in the middle, and then write the formula for the integral as b minus a by 6 and f of a plus 4 f of a plus b by 2 plus 4b. So, all these methods the common feature as you can notice is just that it is the integral become a summation over a few points, the function evaluated at a few points multiplied by some appropriate weight factor. So, all of them actually writes it as some wi f of xi. Okay. So, in the first two methods we had only one point, and then we had the second the trapezoidal rule at 2 points and the Simpsons rule at 3 points. So, these are all. So, all these methods reduces this into an integral will finally become something like wi f of xi summed over I. So, that is what the method finally would become. Okay. So, all of them. So, now we look at some actual a program which actually implements of this rule with various different rules as rectangle rule, midpoint rule, trapezoidal, and Simpsons rule. and compare, get an idea about the accuracy of these methods. So we look at the function of the form f equal to x squared e to the power of minus 2x, some function of this form. Okay. And then we will evaluate the integral. The I of f will be interested in is integral, the limits are 0 to 1, 0 to 1 x squared e to the power of minus 2x dx. Okay, that is what our interest would be to calculate this. So, let us first plot this function and then look at. So, here I am just trying to plot this function between the interval 0 to 1, okay, x squared e to the exponential of minus 2x, okay, and between the interval 0 to 1. So, that is what I am going to plot. So, that is a plot. So, the function is like this. Okay, that is my functional form. So, you have some form like this. I will draw that here again. Okay, so you have x versus f of x, and we have from 0 to 1 which is integral, and it goes like something like this. Okay, so that's what that's the form of that function. Okay, approximately, it's this way. Okay, so now we want to integrate the function from 0 to 1, and using one of the methods which we have just seen. Okay, so we'll go back to that thing. So we want to use one of these methods. So first, let's start with the trapezoidal rule. So that is saying I of f is b minus a into f of a. Okay, so in the first rule we are going to use as trapezoidal rule, in which we would write it as I of f as b minus a, approximate I of f by b minus a into f of a. So now, as I said earlier, that it's this is actually approximating the area under this curve by just a rectangle, right? As you can see, you evaluate f of a and b minus a. So f of a is 0 here. So if you just evaluate just only at this point and then take this integral, you will get obviously a completely wrong answer. That this integral will be 0, right? Because the function is this. So it is evaluated at a equal to 0, because our interval is now a is 0 and b is 1. So if I evaluate this function at a equal to 0, then at x equal to a, it is going to get 0. So we are getting obviously a wrong answer. Okay, so and we know the area under this curve is not 0. So so what we are going to do is to break this up. So the limit, the trivial limit, that is where we take the whole interval 0 to 1 as just 1. Let me just mark this as 1. Okay. The whole interval 0 to 1 as just one quantity, and then evaluate this integral gives us the wrong answer. So then we have to look. We can split this into two for two equal intervals. Let's say we will split this into b minus a by 2, and then do this separately. So that we can do, right? So that is, we split this interval a to b as two intervals, and then apply the rectangular rule for each of these intervals. That is, I would write I of f now. Okay, I of f I will now write as 1 goes from a plus b by 2 to a. So I will have this going from a plus b by 2 to a. So that is a plus b by 2 minus a as the first interval, and the function evaluated at a, and then I have b minus a plus b by 2, and the function evaluated at a plus b by 2. Okay. So that this trapezoidal, this rectangular rule, I split it into two. Okay, so two intervals, and then I will get, now I can see that again this part will be 0 because f of a is 0, but this part would be non-zero, which will be the area of this. It will be area of this rectangle. So again there is error, because obviously this whole area is left out. So you have this error, but then we can improve the accuracy by splitting this into more and more intervals. That is what we are going to look at. So we look at how in the limit, in what limit, how many intervals we need to get a realistic answer to this integral. That is, I of f is 0 to 1 x squared e to the power of minus x dx. So the question to ask is that if I use simple rectangular rule, okay, and evaluate this integral, how many intervals I need, means how many breakups I should do for this whole interval 0 to 1, how many breakups I should do to get a realistic answer. The realistic answer turns out to be 0.80831. So we know the actual answer is 0.80831 to this. So we'll see how many points which we have to use to get that answer. Okay, so that's something which you would be looking at. So look at the program which implements that rectangular rule. Okay, so here is a small program. So this program has this program actually asks for, so it has some, it tabulates the points at x. Okay, x is the number of points in which we are going to evaluate the function. That means it's equal to the dimension of that should be equal to the interval a to b divided by the number of points, which number of divisions which we want. Okay, so that many points we are going to evaluate this function. So we are going to take the whole interval a to b, and we are going to split up that into some number of divisions, and then use the rectangle rule for each of these divisions. Okay, that's the method which you should be looking at. Okay. So this program is to be given an upper limit to the integral and a lower limit to the integral. I have given that as 0 and 1 already. Okay. So here in the declaration of the variables, I have already fixed these values. Okay. These values have already been given. Okay, they are floating points, and but also given the values. So upper limit is 1 and lower limit is 0, and then x is a pointer here, and it's going to be in our array. So before I put in the variables into that, I need to allocate some memory to that. So I use this a malloc function to allocate memory to that. That's here. So x has been allocated some memory using this malloc function. Okay, so let's go into a little detail of that here. Okay, so I will have I'm just printing out the upper limit and lower limit here, so ignore this particular statement. It is just printing out the upper limit and lower limit. Okay, and then here it asks, this program asks for the number of points you want to use, that is the number of divisions you want to use, the number of points at which you want to evaluate the function. Okay, so you enter that here. Okay, so that minus 1 will be the number of divisions. So the number of points you want to evaluate the function at, and that will be read off from the screen as number of n points. Okay, n points is the number of points at which we want to evaluate the function. Okay, so that's in this interval we were just splitting this into many intervals, let's say, right. So each of this interval, so now I will label this as xi's. Okay, so xi, x0, x1, x2, x3, etc. Okay, that's the number of points I want to evaluate. So in this particular graph now I have drawn that 1, 2, 3, 4, 5 points at which I am evaluating this. Okay, so that's the number of points, and once you given the number of points, that many points I have to store in the x variable, right. The x is my array which has this x0, x1, x2, etc. But x is declared as a pointer, so now I need to allocate memory to that before I put in some values into it. So that is here. Okay, so number of points plus 2 into size of float is the memory I have to, because x is a floating point. So I need to allocate memory to that. We have seen this malloc function. Here is the use of that malloc function to allocate memory to this x. Okay, so then now I have the xp is my interval. So I am dividing this into equal intervals. Okay, this interval, this whole distance 0 to 1, I am going to divide them into equal intervals. Okay, so I am just going to say that it is the interval distance is upper limit minus the lower limit divided by the number of points. That is the interval. Then we have xi values. Xi values are then lower limit plus I go from 0 to n points. I lower limit x of I plus x of I is equal to lower limit plus I times the interval, right. So when I equal to 0, it's x of I is 0. So x of I starts from 0, and when I is n points, that is I is the number of points, and then this is equal to the upper limit, right, because xp is at upper limit minus lower limit by n points. So if I substitute that here, you see that at n points it is upper limit, and I equal to n points it is the upper limit, and I equal to 0 it is the lower limit. So x of I goes from lower limit to the upper limit in n point in xp interval using endpoints. Okay, so that's what it is. And now up to this, it should be this part of the program, this whole code up to this should be common for all methods we are going to mention here. That is the rectangular rule, the midpoint rule, the trapezoidal rule, and the Simpsons rule. All of this will use the same part, the same program for all this, except the last part where we actually compute the integral. That is this part. When we actually compute this part, we would change the part. Okay. So now here, let's say we have put an endpoint equal to 1. Okay, there is only one whole. The whole thing is just evaluated only at one point. Okay, then this will be basically 0, right? Because x of I is 0, and we will know that it is this integral will be 0 because f of a will be 0. So now we will see what the accuracy. We will run this program. So you can see that here what I am doing is I am just writing the xp, that's the interval. Okay, now if my endpoints is 1, the xp is just whole of b minus a. Okay, otherwise it's b minus a by endpoints. Okay, so each interval, this is the length of each interval multiplied by the function. The function is x squared. That's power. I am using this power function, which is a built-in in the program part, built-in function in the math library. That is, it calculates the x to the power 2, and exponential, another built-in function, that is minus 2 into xi. Okay, so x squared exponential minus 2xi. So that's what I am computing here. Okay, and I just sum up all this quantities. Okay. So I basically reduce that into the sum. Okay. So b minus a is now split into b minus a by n points, and f of a is evaluated at each of that starting points, and then it becomes a sum. Okay, so it becomes wi f of xi kind of sum. Okay, so it will become a sum like this. That's what I have done. Where wi being just b minus a. So it's a simple weight. The weight is simply b minus a divided by the number of points. Okay, that's the weight wi in this case is. Okay, that's what we see here. Okay, and then I just print out the answer at the end. So this loop which computes that sum is over here, and then I just print out the answer here. Okay, that's the program. Okay, so let's look at this program. Let's just run this, and then this is rectangular rule and minus lm because I am using all those math library functions like exponential and power, etc. So I need that. So I compiled it, and now I run the program. So now upper limit is 1. It's printing out that here the upper limit is 1 and the lower limit is 0. Okay, that's what it's printing out. And it's asking for the number of points you want to evaluate, number of intervals you basically, number of points you want. That's the splitting you want. So let's put it as, let's say 5. Okay. So we get the answer to be 0.067270. So 5 values which we evaluated the function, and we are getting it as 0.067270, while we know the correct answer is 0.80831. Okay, you can do this analytically. You can see that this 0.80831 is the correct answer to this equation, to this integral. Okay, so we have to increase the number of points. So we just increase it to 10. Okay, so we go from 0.067 to 0.74, and we go into 20. So we get 0.77. We go into 100 points, and then we get 0.801. So we are slowly approaching the correct answer, but we have already split this whole interval into 100 subintervals to reach that answer. We still have an error in the third decimal places. Okay. So we need to get 0.808. We are still at 0.801 at 100 subintervals. So we go something like 200. We still have an error in the third decimal place in this here. Okay, this is 0.804 or 0.0804. Sorry, fourth decimal place. 0.0804. Well, the answer is 0.08. Sorry, the answer is 0.0808. That's what the answer which you should get. So we saw that if you use the simple rectangle rule and split this interval even into 100 subintervals, we still are very far from the actual answer to this interval, which the integral, which should be 0.080831. So it takes us a lot of function evaluations and the sum to get this integral correctly if you use a simple rectangle rule. Okay, so now let's do the same thing, okay, using a midpoint rule. So okay, now we will use b minus a into f into a plus b by 2. Okay, so again now we'll use the next one, that is we'll use function value evaluated at f plus a b by 2. Okay, so that's what we're going to use in the midpoint rule. So that means now we're going to evaluate for each sub interval the function evaluated at the middle of that interval. Okay, and then we'll do exactly the same calculation, and then we'll see what happens. Okay, so now here is the program which would use midpoint rule. So it's the same program, no, not very different. The top part is exactly the same. Okay, and now only as I said, where we actually calculate the sum, that is where the change is. S equal to 0 before the loop, and inside the loop we will take the number of points and then evaluate the sum of all the function products. Okay, that is xp multiplied by the function value. Now the function value, now there is a change here. The function value is not evaluated at x of I now. Okay, now I am taking x of I plus 1 by 2. So I want to keep this thing as a constant, that is what we give is the number of points at which the function is evaluated. Okay, so when I say n points, that is the number of points at which the function is evaluated. That's what we are going to give. Okay, and then we are going to use this rule. Okay, so now so again I evaluate, let's say at 5 points. Okay, now I'm going to take this as an interval and that as another interval. Okay, because I need to evaluate this at f of a plus b by 2. Okay, so I'm going to do this as an interval and that as an interval. Okay, so actually when I calculate the function at 0, x1, x0, x1, x2, x3, x4. Okay, and then I will evaluate the function at every alternate points. Okay, so that's what I'm going to do here. Okay, so I've evaluated x of I plus 1 by 2. Okay, sorry, in the middle of every interval. Okay, so I take this interval and I evaluate the function at this in the middle of that interval. Okay, so when I say here the number of intervals is 10, is actually we are evaluating the function only at 5 different points. Okay, so now let's look at this point. So that's f of a, so that is interval b minus a, that is for each interval, that is xp now, that is b minus a divided by n points, and the function evaluated here at the midpoint, that is x of I plus 1 by 2 power 2, right, that is x squared exponential minus 2 x of I plus 1 by 2. Okay, so that is, I have written that way. Okay, so that is exactly this. So if I write this in this form, I am writing this function now as this one. So function is x of I xi plus xi plus 1 by 2. You can see it. So it is xi plus xi plus 1 by 2 the whole squared, right, that is x squared, and e to the power of minus 2 xi plus xi plus 1 by 2, that is x of I. So that is okay, so that's what I am evaluating here. I have written at that. Okay, you could cancel this 2 and 2, but it just for clarity, just to show you that this is actually evaluated at the midpoint between this interval I and I plus 1. Okay, that's where I am evaluating the function. So we will run this program. So before we do that, we will make 2 different output files as we compile the rectangular method, the method we were using by rectangular method. So that program we will compile as and store it as RAC. Okay, so when you run RAC, then I am running a rectangular method. Okay, now similarly I will do the midpoint method, and then I compile that and keep as MID. Okay, so if I run .RAC, then that means I am running the rectangular method, and if I run .MID, then I am running the midpoint method. So if I run .RAC and run it with 5 points, I get the answer as 0.067270, while I should be getting, as we have seen, that 0.8083 831. That's what the answer should be. So, and then we now run the midpoint program, which is again we'll use the 5 points. Actually, when we are saying 5 points here, we are evaluating actually the function at less than 5 points, but we use the same thing here, 5 points, and then we get an accuracy much better than the rectangular rule. So you can see that by simply going to midpoint rule, we have a much higher accuracy, and we have seen the reason for this. This is actually of order the second derivative of the function, this error in the midpoint rule. Okay, so if you run RAC up to 100 in the 100 points, then we get 0.80801. We should get 0.0808. 0.0808 is the answer. We are getting 0.0801. While just running 5 points using the midpoint, we are already at 0.0808. So there's a tremendous improvement in this accuracy by just going to a midpoint method. And now for this particular function. And now we look at the next method, that's the trapezoidal rule, in which we now use 2 points at which the function is evaluated. So we now use b minus a by 2 into f of a plus f of b by 2, f of a plus f of b. So now we are going to evaluate the function at 2 points, again 2 points in each interval. So I will again split this function into, I'll split this function into many intervals, and at each interval I will evaluate at 2 points in this rule. Okay, so that's what going to be the trapezoidal rule implementation. So let's look at that again. So here is a program which does that trapezoidal. So this program, again the initial part is the same. You have endpoints at which it has to be evaluated, the number of intervals, etc. So now here I have changed this. Now I need to evaluate for each interval xp, right, and xp by 2. So at the end of this thing I have a by 2 here sitting. Okay, so you can see that here I divide that by 2, the function. So I have now xp multiplied by the function value at xi, and then plus the function value at xi plus 1. So the two function values. So one is at xi, another is xi plus 1. So let's change this thing a little bit. So I will now write this in the case of the trapezoidal rule. I'm going to write this. The program, what it does is to compute f, the I as I of f is now computed as sigma I xi squared f, so exponential of minus 2 xi plus xi plus 1 squared exponential minus 2 xi plus 1, okay, in the interval xi plus 1 minus xi by 2. So that's our trapezoidal rule. Okay, that's going to be our trapezoidal rule. That's what we are going to use, and each of this for many intervals xi. Okay, so that's what's done here. Okay, so you have this function evaluated at xi and xi plus 1, okay, and multiplied by the dx xp by 2. Xp is xi plus 1 minus xi, and divided by 2 is here. Okay, that's what we're going to run. Okay, so let's run this. Okay, so let's call that when we compile that now. So let's call that as trap. Okay, so that will be, if you run trap, that's we are running trapezoidal rule. Okay, so let's run that, and we get let's use again 5 points. So we get 0.80803. Okay, so compare that with the midpoint for 5 points, and we get 0.80855. Okay, so that's comparable. Okay, so we see that we are not getting much higher accuracy by going to trapezoidal rule and using the same 5-point integration. So far we looked at 3 different methods, that is rectangle rule, midpoint rule, and trapezoidal rule. So now we look at the Simpsons rule. Okay, so that is that where we have 3 function values evaluated. So we have f of xi, and if you have f of xi plus 1 by 2, and f of xi plus 1. So then we'll use 3 function values, okay, and they have different weights now. So now this is, I guess, the first time we are actually using function of different weight. So here again we use function values at 2 points, but both of them have the same weight. But now here we have this function value, this point has a different weight. It's 4 times b minus a by 6, while this is b minus a by 6, and this weight is b minus a by 6. Okay, so now that's that program which does the Simpsons rule is here again similar to this one, okay, except for the last part. Okay, so here is the part. Now we have to evaluate the function at xi, that's the first part here. Okay, so xp by 6 here, so xp by 3. So that is this is a function evaluated at xi, and then there's a function evaluated at xi plus 1, right, that is and then you have a function evaluated at xi plus 2. That's what I'm using. So xi. So now what I'm going to do is I'm going to split this interval like this, okay, and I'm say that this is one interval, and I evaluate the function at 0, x2 and x1. Okay, so 0, x1 and x2 like that. Okay, instead of using the xi plus 1, xi minus 2, so I'm just using the 0, x1 and x2 kind of stuff. That's what. So 3 points. Okay, I need to evaluate the function at 3 points. I do that as xi plus 1 and xi plus 2. Okay, that's splitting this into three different points at which you have to evaluate the function. So remember the quantity, the point is this. It is f of a plus 4 f of a plus b by 2 and f of b. Okay, that's b minus a by 6. Okay, so now my interval has become 2 here. Okay, so that is why I have here x of I put in here divided by 3, because my actual interval b this is actually x of I minus x of I plus 2 minus x of I. Okay, so that is, while xp is x of I plus 1 minus x of I. So I have to put multiply that by 2. So that's what it is, become 3. Okay. So let me write that here. This is what I'm going to do here. I of f now is evaluated in the following form. I am writing it as x of I. So I need an interval. So it is x of I plus 2 minus x of I. That's my interval I'm using, and then I'm evaluating the function at f of xi. Okay, and then I have here 4 times f of xi plus 1, and then I am evaluating it at xi plus 2. Okay, so that's the Simpsons rule I'm using here. Okay, where f is given by each point given by this. Okay, so it is x. So while the dx which I was using was xi plus 1 minus xi. Okay, so this is actually 2 times dx. Okay, so actually this is divided by 6. So this by 2 times dx by 6, that is dx by 3. Okay, that's what I put in here, this program, or dx xp here divided by 3. Okay, so now let's run this. Okay, so when I say now here again the number of points at which the function is evaluated is what we are going to give in the program. Okay, so and then we are going to run this. So we'll now compile this program. We call it simp. We'll run simp. We'll run with 5 points. Okay, and you have an accuracy of 0.0454. Okay, now Simpsons rule doesn't seem to give us very high accuracy, but the number of intervals is of course small. So let's run it with 10 points, and we get 10 points reasonable accuracy. So now this is again 5 intervals. Okay, when I say 10 points, it's actually 5 intervals, because this is one interval for now. Right, but the number of points at which the function is evaluated is 10. Okay, but the intervals is 5. Okay, so we see that in terms of the number of points at which the function is evaluated, for this particular function, this doesn't seem to give us much more accuracy than the trapezoidal rule. But if you look at the interval, then it is as good as the trapezoidal rule, which we get for 10 points. We get 0.0808. Okay, so that's a simpler methods where we actually split the function into various intervals, and then evaluated this function values and multiply them by the distance between those intervals. That's what all these methods rely on. Okay. So now let's go into the next set of rules, which are the Gaussian rules. Right. So now this is something which we discussed in detail in the last class. That is, we now evaluate the function I of f. Now this is slightly different from the earlier methods because we now evaluate the function I of f by writing I of f as so this, again we use a similar finally the integral will reduce into this, but the technique here is writing I of f as not instead of f of x dx we are going to write it as a to b g of x w of x dx, right. That's what it is. So it's a weight function here, w of x. This, and then to distinguish this from this w, we call it a I here. Okay, a of xi. Okay, so now this is some weight function. Now depending upon this weight function and this limits, we had different orthogonality properties, and so of the polynomial. And so we said that we discussed that in the last class, and we said we can have Legendre polynomial if it is -1 to +1, Chebyshev if it is -1 to +1, but we have a weight function 1 minus x square. Here the weight function is 1, and Laguerre if it is 0 to infinity, and Hermite -infinity to +infinity, etc. All these methods, the idea is to approximate the function by a polynomial, okay, and then do the integral, and finally the integral will then reduce to this form. Okay, that is the g function evaluated at xi multiplied by this particular polynomial, and this is Lagrange form for the polynomial approximation. So we write that in the Lagrange form and then multiplied by g of xi. So as I said, what we are going to do is we are going to approximate g by a polynomial. So in this method, g is approximated by pk of x, okay, and which is given by sum over I going from 0 to k, sum product j going from 0 to k, j not equal to I, right, x minus xj divided by xi minus xj into g of xi. Okay, so that's what the approximation. So g here, so we write the integral in this form and then choose the appropriate w for depending upon the limits, okay, and we write the polynomial. This is approximated by a polynomial p, okay, which is given by this quantity, okay, and that was the basic idea of this integral. And then the weights, then we can write that as ai g of xi, and the weights given by the integral of this part, right. So now the g of xi comes out of this integral because it's integral over dx. Okay, so it's only the function of x, integral over x. This is the only part which is a function of x, so we can take that out. So then we can write this in this form with a of I given by this quantity. Okay, so now we have seen that the way to go about this is because of the orthogonality properties of the matrices, that if you want to get very high accuracy using this, that is, if I choose a kth order polynomial, I can get accuracy up to 2k plus 1 order in derivative, provided I choose these points, right, these points xj's at which the function is tabulated. Okay, now the function has to be tabulated at some values, and that tabulated points, if I choose them as the zeros of a polynomial, depending upon what the limits and the w is. Okay, so for example, if it is the limits were -1 to +1 and my weight function was 1, then I would use the tabulated points as the zeros of the Legendre polynomial, okay, and similarly for other cases. Okay, so that's the method. So first part in this thing would be to write the integral which we want to evaluate into this form, in this one of these forms. Okay, so we have to change the limits such that the limits are -1 to +1, and we write that in this form. So that's what we had seen, okay, in this particular example. For example, when we want to, this is a particular function of interest right now, we just want to evaluate this integral, that is x squared e to the power of -2x, okay, and then I have to change the limits of the integration from 0 to 1 to -1 to +1, and that I do by changing the variable from x to t by going from -1 to x to t, that is t equal to -1 plus 2x, and then I can write the integral now I as 1 by 4 minus 1 to plus 1 1 plus t whole square e to the power of 1 plus t dt. Okay, and then evaluate the function, and now this function is evaluated at various values of t, and those values of t are the zeros of the Legendre polynomial because of my limit, and the weight is 1 here. So that's the idea. Okay, now I hope this is clear. So we want to use the Gauss-Legendre method. Then this function, this integral is first converted into minus 1 to plus 1 by a change of variable. Okay. And then this function here, now 1 plus t square e to the power of minus 1 plus t, is tabulated at different values of at the zeros of the Legendre polynomial. Okay. And the appropriate weight functions are calculated using for example this value. Okay, we don't use this value actually. I'll come to that a little later. Okay, but so that's the appropriate weight functions are calculated, and the functions are evaluated at that point, and we do a sum of all those functions. Okay, so now here, for example, I summed over 4 points, that is x0, x1, x2, and x4. So this x0, x1, x2, and x4 should be the first 4 zeros of a fourth order Lagrange Lagrange polynomial. Okay, sorry, Legendre polynomial. Okay, in this particular Gauss-Legendre integration, which is f of x integral minus 1 to plus 1 f of x dx with w equal to 1. So it's just f of x dx, or f of t dt in this particular case. Okay, that's what we want to look at. So so remember that is so you can also incorporate that change of variables into the program itself, and now we want to evaluate in the program in terms of x itself. Then what you could do is instead of you could tabulate the t's as the zeros of the Legendre polynomial, and then evaluate this function at 1 plus x0 by 2, 1 plus x1 by 2, 1 plus x2 by 2, because the relation between x and t was t equal to 1 minus 1 plus 2x, or x is equal to 1 plus t by 2. Is that's also possible, right? So that's what we have to do. Okay, so now we come to the computation of the weight. Okay, so now we know where to choose the x to be. Okay, so now the functions are evaluated, tabulated at the zeros of the Legendre polynomial in this particular case, because again I repeat, because we are going to use a minus 1 to plus 1 interval, and the weight is 1 here of the function. So now the question is, how am I going to compute this weight, because this weight itself involves an integral over minus 1 to plus 1. Okay, so if I use this form, this is not very convenient, because because I have to integrate this from minus 1 to plus 1. So this weight itself involves an integral, so I will not gain much advantage. But it's not so complicated, because what we can do is we can actually write this particular function in terms of the Legendre polynomial itself. Okay, and then we write the w as in this form. So what we have seen so far is that we have to write it in this. We can write it in this form, and we said ai is now given by integral a to b, right? And or in the particular, in this case, if suppose we converted the limits etc., then it is minus 1 to plus 1. Okay, sigma for each of this, and pi j going from 0 to k, j not equal to I, x minus xj divided by xi minus xj. Okay, so that's actually the weight which we have to compute. Okay, dx. Okay, that's what the weight which we have to compute. Okay, now this involves integration, so that's not something which we want to do, because our idea is to actually do another integral. So it doesn't make sense to compute the weights by doing another integration and then doing a sum. So we have to change this form. Okay, and it turns out that this can be actually written as in terms of the Legendre polynomials, whose zeros we have used here to tabulate the function value. Okay, or this f of xi here is actually tabulated at the zeros of this polynomial, of this Legendre polynomial, and in terms of the Legendre polynomial we can write this weight, and this that turns out to be 2 divided by 1 minus xi squared into p k prime, p k plus 1 prime of xi, p k plus 1 prime of xi whole square. Okay, so now that's the derivative of the k plus 1th order Legendre polynomial. So I should say one more thing. So that actually if we choose this, there is an order difference between these two, because these are now tabulated values. The xj's are the tabulated zeros, like zeros of the legendary polynomial. So this goes from 0 to k plus 1, k. So that's of order k plus 1. So I am using that polynomial, legendary polynomial here. Okay. So I can write this. I don't go into the details here of how you go from this to this, but you can write the weight as the weight at I of a of xi as 2 divided by 1 minus xi square into the derivative of the k plus 1th order polynomial at xi, evaluated at xi in square. So now this is a form which you are going to use for this computation. So once we know the zeros and the corresponding weights, okay, then we can just simply compute this sum and then we get the integral. Okay, so that's something which you would look at. Okay, so now the question is, how do I compute this derivative? Okay, and how do I evaluate the function at various points? So how do I compute the weights is question, and then how do I know the zeros of this polynomial? Okay, so I said that I need the zeros of the legendary polynomial here. Okay, that's where I'm going to tabulate it, and I need the derivative of the legendary polynomial. Okay, so now these two things are required to actually compute this quantity. Okay, but remember, both of those doesn't depend on the actual function value itself. So once you can actually construct a table of this quantity and keep it, and then you can use it for different values of the function. Okay, the only thing is we have to rescale the variables for different functions and different limits. Okay, and that's the only thing which you have to change. But these ai's and the xi's are independent of the function values. Okay, so we can actually compute that. Okay, so now the question is, how do we evaluate the derivative and the zeros? Okay, so to evaluate the zeros, of course we have seen the earlier methods. We can use something like Newton-Raphson, okay, to find the zeros of the polynomial. Okay, so if I know how to evaluate the derivative of the polynomial, and then I can use Newton-Raphson to get the zeros of the polynomial. So I just make a guess value for the 0, and then I write p of x plus delta x as p of x, okay, p being the polynomial of some order, okay, plus p prime of x, right, into some delta x, and then I say that this should be my 0. Okay, so then I get delta x as minus p of x divided by p prime of x, right, and then I add this, and the next point would be, so I start with a guess value for x, and then I go in the next iteration as x plus delta x as my guess value, and I repeat this quantity till the p goes to 0. So that's a Newton-Raphson, simple Newton-Raphson scheme. Okay, so I have all the tools. I know the Newton-Raphson to get the zeros of the polynomial, okay, and if I know how to compute the derivative of the polynomial and how to evaluate the polynomial at that particular value of x, then I can compute this integral here, right? Okay, because I can find the zeros using Newton-Raphson, and but the only thing which I now need is the evaluation of the function p of x and its derivative. And for that, we again use some properties of the legendary polynomial, the recursion relations, which tells us that the relation between the jth order polynomial and the jth order polynomial and the j plus 1th order polynomial. Okay, so the recursion relations connect polynomials of different order, okay, by a simple linear relation. Okay, so that's what we're going to use. Okay, so we're going to use the fact that the recursion relation that j plus 1 in p j plus 1 is equal to 2j plus 1 times x pj minus j pj minus 1. So that's what the recursion relation is. So it connects the jth order polynomial with the j plus 1th order and the j minus 1th order polynomial. Okay, so this is a relation which we can use, and we know that p of 1 is 1. Okay, so that's also something which we'll use. Okay, and then we'll start from this and then compute any polynomial of any order you want at any value x. Okay, so p of 1 is 1 for all x values. So now if I want to evaluate polynomial p10, okay, then I will start from p of 1, and then I'll just keep on doing the recursion relation and obtain the I use this recursion relation to obtain the next higher order polynomial values. Okay, that's something which I can use, and then I have this relation that Pj prime is given by j into x Pj minus Pj plus 1 divided by x squared minus 1. So, this is another quantity which I can use. Okay. So, I have basically the recursion relation to compute the p values, okay, and another relation which connects the derivative of the jth order polynomial to the polynomial, the jth order polynomial and the j plus 1th order polynomial. Okay. So, and I know how this is connected to this through the recursion relation. So, I can actually compute all these quantities, and then once I have the p and the p prime, I can actually get the zeros of the polynomial, and once I have the zeros of the polynomial and the derivative, I can compute the weights, and once I have the weights, I can compute the integral. Okay. So, that is a whole scheme. Okay. So, now we will just see the implementation of this in a program. Okay. So, that is slightly more complicated code. Okay, so now this is the program here. Okay, so again, so the first part of this is the same, that it actually asks you how many number of points you want, etc. And then this function again allocates memory for different functions like weights. Now we need to store the weights, and the weights, and this x is the function values, and xp is again the values at which we have to tabulate the function. Okay. So once we have that, we can just call a program. So now you see, as I said, this is independent of the function, right? So the weights and the points at which it has to be tabulated is independent of the function. Okay. So in the beginning of this program, okay, I just call a function, another function called Gauss Legendre, okay, and I supply the lower limit and the upper limit, okay, and then this program would then return to me the x values and the weights at the number of points which I have given it. I asked the program to do it. Okay. So what we need to actually find out is how do it computes the x and the w, that's the points at which the zeros of the polynomial, and rescale appropriately because I have given the limits as this, and then weights of the function at that. Okay. So now if you know how to compute it at between -1 and +1, then we know by simple scaling we know that we can write it as in this fashion. This is the zeros of the polynomial, then I know where the function has to be evaluated by just simple a plus b by 2 minus a minus b by 2 into xt. So that's not a big problem. Which we will find out is the zeros of the polynomial. Okay. So that's what this Gauss Legendre actually does. Okay. So I do the computation of the zeros of the polynomial by simply using the this method, that is this Newton-Raphson. Okay. So first I have to evaluate p of x, and then I have to evaluate p prime of x. So p prime of x is given by that. First I have to get the p of x. Okay. For any order I have given. Order is what the number of points I am going to ask for it is. Okay. So if I say number of points is 4, I have to do a 4th order Gauss Legendre. That's I need 4 points, etc. Okay. So now this is what this part is doing. So it has a simple guess value for the 0. Okay. So it has a guess value for the 0 which is cos of pi into I minus this is the ith 0. Okay. Ith 0 is guessed as pi into I minus 1 by 4 divided by n plus half. This is simply a good guess value where it actually works. Okay. And there are better methods of actually guessing the zeros of a Legendre polynomial. We will not go into those details. So we are making some guess value of z. Okay. And then we come down, and then we just compute the now here. So I am just saying p1. So I just start with p1 equal to 1. That I know, and I put p2 equal to 0, which I don't know what it is. Okay. And so I just put p2 equal to 0. So p1 is 1. That is something I know. That first order polynomial is 1. Okay. And then p2 equal to 0 I start with and initialize p2 equal to 0, and then I compute as in a loop for all the way up to n, where n is the number of points at which I want to the order of the polynomial. Okay. That is the order of the polynomial is n. That is n points is taken as n here, and then I just use this recursion relation. So you can see the recursion relation here. Okay. So that's the recursion relation I am using. So 2 times j minus 1 into the guess value x. Okay. So it is I am using that's recursion relation which I have written down here to compute pj plus 1 from pj. Okay. So that's what I am using here. Okay. So that recursion relation is used here to compute the value, and I do this loop till I reach the order of the polynomial I want to evaluate. Okay. So n is the number of points I want to evaluate the function n. Okay. So I do this till the order of the polynomial I reached, and then I use this the derivative of the function here. So this is the derivative of the polynomial, which is computed again using that formula which I have just written down. Okay, so I use this formula to compute the derivative of the polynomial, because I already use the recursion relation to compute p1 and p2. Let's say, then I can get the p1 prime, or if I use fourth order, I can get p4 prime from p4 and p5. Okay, and I can compute p5 using this, starting from p1 equal to 1 and using the recursion relation. So that's all it is, and then I improve on the z by using this Newton-Raphson here. So I compute z1 as z1 minus p1 by pp. So pp is the derivative and p1 is the function, is the derivative, is the polynomial of the desired order I wanted. Okay, I am just using p1, but it is a polynomial of the desired order I want, because I gone through this loop n times in the recursion relation, and I obtained the p1 is now my order of the polynomial I wanted to get, and then I can use this to get my zeros. Okay, so now the zeros are tabulated here for different values. Okay, and the corresponding weights are then calculated using this formula, that is 2 by 1 minus xi square into p prime. So once I get the p prime and the p, this is pretty simple. Okay, once I got the zeros and the function and the polynomial derivative in that form, okay, then it is extremely simple. I can write that down as the weights. Okay, and then this program just returns that weight into the main program. Okay, so then I'll just compute them as a, and then I just simply sum over the weight into the function evaluated at that xi values. Okay. Now as I see that this xi values are actually rescaled by here. Okay, I rescale them. Okay, so xi values I get is actually values which are rescaled. Okay, so x sum into the rescaled values. Okay, that's what I'm getting. Okay, in the actual derivative in the actual interval a to b. So we just run this program now. Okay, so g. Okay, so we'll just run it between the limits. Say now we'll just run a 4-point Gauss-Legendre. So we just run a 4-point, and you can see that we get amazing accuracy. We get 0.80830 by just running a 4-point Gauss-Legendre. So we could get even pretty good accuracy by 3. So with 3 to 4 is a tremendous improvement. So by 4 points we are getting a tremendous improvement. That is, the actual value you remember is 0.080831. Okay, that's the actual value. We already got up to the 6th decimal place by just doing a 4-point Gauss-Legendre. So you can see that this method is the most accurate, okay, provided you can tabulate your function the points at which you want to use. So we stop that here. So you could actually compute this yourself for different functions and see how compare this with the Gauss-Legendre with other simpler methods, and then and compare the accuracy you obtain. So the next lecture we will look at how to solve differential equations. The next step is to actually look at differential equations. So we will look at that in the next lectures.